Hi, my name is Tuomas and I work as a RSC at UCL in London. I'm going to talk about my first experience using Julia in an HPC project developing a package for tsunami forecasting using data assimilation, a technique for combining numerical models and data commonly used in numerical weather prediction. I've done this work with my colleague Mose Giordano, as well as scientists from UCL and the Alan Turing Institute. While this video shows a visualization of our code simulating data from another model and reconstructing its state, I'll talk about why we chose to use Julia for this project. We wanted to use a language that allows us to develop prototypes quickly for the scientists to test and give us feedback, and that is useful to the scientists after our collaboration is over. In addition, Julia has a good native implementation of linear algebra that we heavily lean on and has a track record of being used successfully in HPC projects. We use a data assimilation method called a particle filter. It consists of 4 steps, which I'm showing in this cartoon. The model consists of multiple representations of the true state of the system called particles. After making an initial guess for the state of each particle, they are updated in time, compared with an observation of the true state, weighed based on their likelihood of representing the true state, and resampled back to uniform weights. Our implementation of the algorithm does all of its parallel communication in the resampling step, which allows the rest of the algorithm to run very efficiently on parallel processes. The communication is handled by Julia's MPI.jl package, which you'll probably hear about in this conference. We're very interested in the parallel weak scaling of our model. I'm showing here a measurement made on the CSD cluster at the University of Cambridge. You can see some technical details on the left. For these benchmarks, we were using Julia 1.4, so things may even have improved by now. This figure shows that we get reasonably good parallel efficiency of almost 90%, running on 4,000 processes with around 260,000 particles. That is, 260,000 copies of our numerical model are being updated in parallel. I leave you with a couple of links. Please get in touch if you're interested in our project. Thank you for listening.